Thank you for introduction. Hi, everyone. As nice introduction, my name is Solmaz, image analytic, algorithm software developer in LemnaTech. Today, I'm going to talk about our development in machine learning and our new approach to use sensor fusion to improve the classification result. As everybody knows, the challenges we are facing in food security are high, and we have 2.8 billion more people to feed by 2050. In addition to the increasing in population, we have increase in cost and labor in the agriculture research, and also agriculture itself. So we have decrease in total land and climate change. All of this comes to the conclusion that we need to have 75% more agriculture product by 2070. For audience here, I don't think that I need to explain more about the importance of agriculture, but think for a moment. It took me 1 minute to talk for introduction. In that 1 minute, 25 people died just because of hunger, and 15 of them was just kids. So what's the solution? How we can solve this for the future? Our vision in LemnaTech is that we are trying to harvest the data, especially field data. We are trying to digitalize and phenotyping data, which is the best way to estimate the yield in agriculture. It was a lot of talk about, introduction talk about artificial intelligence and machine learning. I don't talk a lot about what that means, but the idea behind machine learning comes from how we can train programs and machines to learn from their experiment, exactly as how human learns from their experiments. So we are trying to program the machines and to be able to predict and to learn from the experiment and improve it. So in our case, experiments is our data set. For increasing the yield, it's a lot of components involved, starting from genetic, soil, irrigation, climate, and all of them can be seen as yield improvement can be seen in phenotypic data. There's a lot of different platforms to improve, to see the plant change growth rate in laboratory system, greenhouse systems, or field. But the most reliable system is a field system, so you can see exactly how your crop is changing, basically because it's a field environment and real-time data set you can collect and process the data. So I'm going to talk about field scanalizer system. This is a project we are involved in, and we are working with Department of Energy, ARPA, under the project called Terra. That's our gantry system, and we have the model. You can see the model, a small model after the talks here. So we have the model here. The gantry system is included in a camera box that all the sensors is inside the camera box here. And it's moving in 3 dimensions in the field. And is able to reposition it at millimeter level accuracy. We have quite sweet range of the sensors in the camera box, starting with stereo RGB, thermal data to measure the water content of the plant, laser scanner. The data you can see here, it's few days after the emergence. So you see the amount of details that you can see. The plants are about 6 centimeter height. PS2 for measuring chlorophyll content of the plant, and hyperspectral camera. Next talk is from Hedwall. They're going to talk more about Hedwall, about hyperspectral camera and how we can use it. This dataset shows a sample of how gantry data, 3-dimensional point cloud data will look like in the field system. So this is the data it's collected from the whole field, and it's color-coded. So the ground is blue, and the plants get taller, and the higher tallest plants are in red. So you can see the difference even in different part of the field, and different plots has different height, and this shows the genome difference between different plots. So as the example, you see here the different plots that has different height distribution. So it gives you a lot of detailed information. For our field scan analyzer, we are looking about 5 to 6 terabyte data per day. So we have a lot of data to analyze it. Next slide shows better information and details on how the plants are growing. So this shows the plant growing from starting the season to the end, and you see the details that you can get from the 3D scan data. Okay, how machine learning can help us? There was a lot of examples that, of course, everybody knows. Game playing, search engine recommendation system, speech recognition, face recognition. Recently, a lot of machine learning algorithm has been used in autonomous cars. But something more interesting is that machines can learn even how to cook just with watching YouTube video. This is true, and there's a talk that people are concerned now about robots being more intelligent compared to humans. So you can get a lot of information from just machine learnings and how they can work on. This is, when I was a kid, I used to play Mario. And it was my favorite game. So this is showing that how the computer can learn and play Mario. This is not a human. This is a computer is playing. So it's using a machine learning algorithm, and it's using the scores that you get as a training and cost function. So it's trying to improve and get more score during the time. The algorithm is going through different generation. In the first generation, the Mario is just stop and try to figure out if it's going to move. Should I move, or should I go one step to the right, and trying to click the different options that he has. So for the first generation, it's just stop. After a few seconds of stop, it's figure out, okay, if I click on the right, I can move. So you can see the white dot shows the path that the Mario can pass, and the black dot is representing the insects or the animals that is going to kill him. So based on the few generation, the Mario is learning and to how to improve and how to pass the lines. And this is showing the examples how it's clicking and using the key. It's a really nice video. You can search for Mario in machine learning. You can find it in YouTube. It's a 5-minute video, so I encourage you to watch it afterward. So in LemnaTech, we are thinking about providing algorithms for everybody. Even if you're not able to program, it's going to be easy to use. So it's hard for, I mean, if it's easy even for my grandma to program. For machine learning approach, we start with training data. You have your data. For example, you want to detect the plant from non-plant, or you want to classify your different type of plant or fruit. So we are starting with adding the sensor training data and labeling, point of the interest. If you want to detect disease or objects, you can just click and just select the area that you want. In the next step, you're calculating the future. For future extraction, you can use color information, texture, key points, shape, edge, or even if it depends on the sensors that you have in the system, you can use different vegetation indices or wavelengths if you have hyperspectral data. After the feature extraction, it goes to the classification algorithm. You have different options to choose from: support vector machine, random forest, boosted tree. What is the best way? No one has an answer. Which algorithm gives you perfect way? So you have the option to choose from the different learning algorithm and train your algorithm. After you train your data set, the new data comes in. You don't need to choose the label. That's the main, of course, that's the main reason. It goes through the same feature extraction, and go through the classifier, and you get your data as a classified result. So as I said, it's simple as exactly how I explained. You just need to drag and drop and make your system and run your data set through the system. It's easy and user-friendly. This shows one example in the 3D data. So it's segmenting plant. This is a wheat data. It's trying to differentiate between ear and the rest of the plant. So it's easy, even if you label in the training set the stem and leaf, you are able to detect the stem and leaf with good resolution. This is another work. It's from a conveyor system. So it's an indoor system, and plants is going through different chamber when we are taking the pictures from the plant. So in this algorithm, we are trying to detect plant from the background. Most of the algorithm that now is available, they are using semi-automated system based on just thresholding and choosing what's your RGB is. We are looking for the green pixels, and okay, background is white, and then subtract that. No fall green and RS aposty from Danforth Center, they're part of the Terra project. We're working on the system. So they're using the convolutional neural network, TensorFlow, Google Brain. So they're using training the system, just your data is going through different layers and classified. Your input is image pixel and output is plant, non-plant. And you're able to train all the data jointly. So this is similar. You see it's one segment of the plant is going through the convolutional layers, and you are able to detect the plant from the background. This shows the example. In the bottom, you see that it's even high with human eye to detect the plant from soil and pot inside. So after the few iterations, you see that how good you are able to detect the plant from the background. So the approach we are looking at is using sensor fusion to improve the classification result. Any non-trivial machine learning algorithms need high quality and good training data set. And this increases the demand to use different machines, different sensors with different temporal and spatial and spectral resolution. So sensor fusion is a process that we are integrating data collected with different sensors at different spatial and spectral times and temporal scales. And we are putting all the data together as one data set, which can contain more information compared to each single sensor. So I show you an example. This is again from the conveyor system. We have the RGB, but it's in gray scale. And we have our thermal data. So if we start with overlaying data, you see there's a little shift. These two cameras mounted at the same distance to the plant and using the same lens, but still you see a little difference between two sensors when you are trying to overlay. So we are using sensor fusion, and we get a perfect match for when you overlay the data on each other. So what this can be used? Detecting plant from background in thermal imaging is hard, especially if you're looking at the field data. So it's easier to use the RGB mask in this way to detect a plant from the background. In addition to that, IR data can be used as a forced channel for your RGB data and use it in the machine learning algorithms. So it's not limited just for two-dimensional. Even in three-dimensional, we can use the RGB and 3D fusion. So this shows the overlaying and mapping the data from RGB and 3D scan. So you see the amount of the data you get, and it's easy to detect the plant from the ground and also stem and different part of the plant, because you get the architecture from the 3D scan and you get the RGB color-coded pixels. This one shows the fusion from thermal data and 3D. The next slide shows better how you will see the difference. So this scan is done from 9 a.m. to 2 p.m. In the morning, the temperature of the plants are higher compared to the ground, but as we go to the end of the scan. This shows, these scans are done around 2 p.m. So these parts, the ground are has higher temperature compared to the plant. So when we are doing the overlaying data from the thermal data in 3D, you easily can detect the plant from non-plant. So we are trying to use a fuse data to classify or to use a better classification. And this concludes my presentation. I talked about the accuracy of target detection that we got with machine learning, and the future that we think is in sensor fusion, using different sensor to provide enhanced and structure from the data. And you get, in addition to getting better training system, is also fusion can be used for calibrating hyperspectral data, so it's easier to correct for plant architecture and the leaf angle. If you have any question, I would be happy to answer.